first one is calculate the root of the function, that is x cubed minus 2 sin x, using bisection method. So you need two initial guesses. So initial guesses are like 0.5 and 2 that are given here. Okay, and you need to perform 5 iterations and report the solution obtained. Okay, so this is a simple hand calculation which you can do. You can prepare the same table as we have done in the class. Okay, then the second one is you are given the relationship between the area ratio A by A star and the Mach number for flow in a nozzle, and this nozzle happens to be a convergent divergent nozzle. Okay, so on the right hand side you have Mach number m, which is in m square, and then m is raised to the power of square and gamma plus 1 by gamma minus 1 and so on. So you have some nonlinear expression on the right hand side. On the left hand side, what you have is A by A star square. Then given A by A star, the task is to determine m from the above equation. So you need to calculate, the left hand side is given, you need to calculate what m would it satisfy to get the corresponding A by A star. Okay, or in other words, if we know the area ratio, then what will be the Mach number of the flow? Okay, now so essentially, because it is, this equation is in m square, there are two values of m for a given value of A by A star. One value will be less than 1, which basically corresponds to a subsonic, that is a flow that is happening at this is a typo here, subsonic SYNIC. This is supposed to be a flow that is happening at less than the speed of sound in that medium, and then another one will be greater than 1, m will be greater than 1, that is going to be a supersonic value. Now, taking gamma equals 1.4 and A by A star equals 10, compute you are asked to calculate the supersonic Mach number. Okay, that means whatever is the value that comes out for m greater than 1 using Newton's method. So you would basically now write this as a function, then take derivative of this function, and then use the xk plus 1 equals xk minus f of xk by f prime xk. You remember the Newton's method iterative formula. You would use that and then calculate the Mach number value. Okay, now initial guess value is given. You can take m equals 2.0. So because we want to calculate the supersonic Mach number, the initial guess is given as more than 1. Okay, but if you want to calculate the subsonic one, we would take the initial guess to be preferably less than m less than 1, so that we will converge to a subsonic Mach number. Okay, and then you're asked to perform 6 iterations and then present your results in a tabular form. So we have done some example problem on this, so you can follow similar lines and then do these two problems as hand calculations. And the programming one, again, it is basically the Newton's method. Write a program for Newton's method that takes in a function, its derivative and initial condition, and an error tolerance. So we already wrote the pseudo code. You just need to follow that in the program that you will write in MATLAB. Now, once you write the program, you need to calculate the root of the following function with given initial guess value. So essentially, the first one is, so you should be able to put in two functions. First function is tan t plus t with an initial guess of x naught equals 7. Okay, and then the second one is g of t equals e power t minus square root of t plus 9 with an initial guess of 2. Okay, now for each of these functions, perform 15 iterations. This is a program, so it doesn't matter. So you can easily run 15 iterations and report the values. Okay, containing the again, you can print this output as an iteration number, solution, function value, and error in a tabular form. Okay, so this is I think the programming part is much simpler compared to the what we had for assignment 1. Okay, so in that sense, it is much easier. Okay, and much more straightforward. Okay, so this is about 12 days. So it will be due on 22nd of October. I think that will be some that's on Wednesday next week actually. Okay, fine. Any questions on the assignment 2?
So one question I have.
Yeah.
Just one thing that I was trying to solve problem number 1 and 2, so I could solve 2, but problem number 1, just want a clarification from you that when I'm calculating gx at 0.5, okay, taking x as 0.5, then
x is in radians here. X is in radians.
So basically, we have to just 0.5 multiplied by 180 divided by pi, right?
Say it again. 0.5.
0.5 multiplied by 180 divided by pi. So that value you have to put.
No. 0.5 is, I cannot hear you properly.
0.5 multiplied by 180 divided by pi. That will be radian,
no,
right?
you can do that. Then if you do that, that will only go for the sine of x. X cube will still be 0.5.
Yeah, That's what I'm telling you. I'm talking about only sine of x only.
Okay,
That's
otherwise otherwise you can use sine function to read in radius, then you can directly give 0.5.
okay. I could not get it, sir. Can you repeat, please?
So you can directly use sine function, but then in your calculator you can change the mode from the input mode for sinusoidal functions to be instead of degrees, you can change it to radians.
Okay, cool.
Both are fine. Either you want to convert it to 180 by pi and then use it, or directly use the radians mode for all the trigonometry functions. Both should work.
So even in exam also, if it comes, then we have to consider trigonometry radian only, right?
Radians, yes.
Cool.
Yeah, because it's not in degrees. Yeah. So otherwise it will be given. I think I have not written here. Otherwise I can give x is in radians. Okay, I'll probably mention that in the exam. Okay.
Fine, sir. Fine.
Yeah.
And even in exams, sir, this type of problem is likely to be asked in that way, right, sir?
Yeah. I mean, essentially, see, when you are doing these hand calculations, because these are going to prepare you for the exam.
Noted, sir.
Right. So because I mean, so you're doing your programming parts because you have to get accustomed to programming, and then we should also translate, or whatever theory we are learning in the program, pseudocode we are learning, that should be translated into a working program on your side. But we don't have a programming exam as such, so and we don't have a project as well. So the learning for programming, and the main takeaway will be how do you translate all this into a program. So that will come through these assignments. Of course, to prepare you for exam, we have these hand calculations, which are supposed to prepare you to solve problems in the exams.
Noted, sir. Thanks.
Okay, thank you. Any other questions, anybody? Okay, then let's get started with our lecture. So I hope you are now able to see my second. Are you able to see my screen? Yeah. Okay. Are you able to see my blank screen here, which I usually write?
Yes, sir.
Okay, good. All right. So, okay. So as of last lecture, we were learning, or we did the how to obtain given a stencil, right? So we are essentially in the basics of the finite difference method, and we ended up constructing one-sided, right? That is basically forward schemes, right? And also backward differencing schemes. And then we said you can also construct what is central difference schemes, right? So this is CDS, FDS, and then BDS. These are different schemes that we constructed. So if you are essentially going to use I plus 1, I plus 2, and so on, we call that as forward difference schemes. And then if you are going to use I minus 1, I minus 2, etc., we call this backward difference schemes. Whereas if you're going to use I plus or minus 1, I plus or minus 2, and so on, we call such stencils as centered stencils, and then the schemes we call them as central differencing schemes. Okay. Now, as you saw from the last lecture, this calculation of or calculating a derivative, right, to let's say the rth derivative.
Professor, I have a question regarding that previous class. Can I ask?
Sure. Yeah, please go ahead. Yeah.
The source of error that you have taught now. Like sources of error.
Yeah.
So you have taught about what I mean to say is a truncation error.
Right.
So there will be a solution to the equation which is exactly matching 0, 0, which is continuous in nature.
Correct.
But when we are approximating that, what I mean to say is, then it becomes algebraic. We discretize a function, and then we obtain a solution of what I mean to say is x, y, and z, which is very near to the exact solution.
Correct.
And the difference between these two is called truncation error. Truncation error, if I'm not wrong, right? Sir?
No. So this is, I have written here f of phi. This is basically the governing partial differential equation or ordinary differential equation or some other equation, right? That is our equation, right? F of phi basically contains f of phi partial x, all sorts of things equal to 0. This is our continuous analytical equation, right? This is our analytical equation. Now this has a solution that is little phi, right? But then
Yes.
once you have discretized, you got another equation which is capital phi of capital phi bar. Okay, capital F of capital phi. This is basically your something like your it could be in terms of phi I, you know, and so on. These are basically discrete values, and then you have an algebraic equation. This could be a linear algebraic equation or a non-linear algebraic equation.
Yes,
right?
right.
These are again algebraic equations. Now the thing is that this little phi will satisfy the partial differential equation exactly, right?
Exactly. Yeah.
So it's going to give you 0. Similarly, this capital phi I is going to satisfy your discrete
Algebraic equation.
algebraic equation exactly. That means f of I, phi of I is also going to be 0, right? But then your continuous function phi is not going to satisfy your algebraic equation. So essentially your capital F of little phi will not be equal to 0, right?
Yes.
This is what we call it as a truncation error, the amount by which the exact analytical solution
will not be able to satisfy the algebraic equation.
Algebraic equation. That is your truncation error. Okay.
And sir, you have defined a term called norm also, if I'm not wrong, right? No, sir?
Yes. Yes.
So truncation error is nothing but the modulus of, or I would say norm. So it could be L1 norm or L2 norm, something like that. So, sir,
no, that is not. Yeah, that is not truncation error. The norm was something different. Okay.
Yeah, I got the point, sir. So basically, I wanted to just ask you about that little bit more about that norm, sir. Can you just
Sure.
what I
Yeah,
mean
no
to say, elaborate a bit on that, sir? I'm sorry for.
Yeah, no problem. So norms. So norm is basically a way of finding the magnitude of either a vector or a matrix. Right? So if we have only one value, let us say I have a value of E equals 10 or something, we know that we don't have to calculate any value. We know that, let's say, error equals 10, error equals 100, and so on. We know that this is the magnitude of the error, right? Error magnitude. But then if I have, let us say, error as a vector, you know, E bar equals, I have some 0.1, 10, 0.2, 5, and so on. So how do I say what is the value of the error? Because I have several errors. Similarly, I could have these things in a matrix form. So that's where we define a norm for a vector, right? Which is basically, it could be a infinity norm, it could be one norm, it could be two norm, and so on, right? What we said, but if it is infinity norm, it is basically going to be just the maximum of the vector. That means whatever the maximum value of the x is, what we're going to call it as the infinity norm. Similarly, we said one norm is going to be the, I think we said this is basically the summation of the x or something like that, right? So summation of the x. If it is two norm, we said it's going to be sigma mod x square, square root, and so on, right? So that is how we have defined the norms. Basically, they are going to define a magnitude for the vector that you have, so that you can get a single value. With that value, you can say whether the error is actually increasing or decreasing, although your error is actually a vector, or it could be a matrix. So that is the background behind the norms.
Okay, sir. Understood, sir. Thank you so much.
Okay, no problem.
Thank you, sir.
Thank you. Anybody, any other questions? Okay. If no more questions, let's get back to this thing. So we said if you want to calculate rth derivative mth order accuracy, we essentially said, given a stencil, we can find out how to develop an expression for a derivative, right? The derivative could be first order derivative like dou u dou x. It could be second derivative dou square u by dou x square, and so on. That is what we have done. But then as you can see, as the order of accuracy increases, or the derivative rth derivative increases, this process of what we have followed can get very cumbersome, right? Because we are writing several equations and then so on. So there is a compact form available, which is basically using something that is known as a Taylor table. So we're going to, instead of expanding out all the terms and then writing it that way, we're going to take a little bit of a variation of whatever we have done in the last class, but project it or present it in a nice table form. So these Taylor series terms that we have, we're going to write them in a nice table form so that we can easily infer from there. Okay, so that is the first motivation. The other motivation is basically, given a stencil, can we find out what is the maximum possible order of accuracy that we can obtain for a derivative? That means let us say we are asked to calculate what is the maximum possible order of accuracy for a second derivative on a particular stencil. That means we are already fixed how many values we should use. Let us say if you're given I plus 1, I plus 2, and so on. So this is not very different from what we have learned. It is basically going to be the same as before, but then the entire process is going to be slightly different or presented in a much more compact way, so that it can be extendable for other kinds of derivatives, okay, or higher derivatives to higher orders of accuracy. It will be very straightforward. So we're going to look at this one. So that means the question we are trying to ask is essentially, if I want to calculate, let us say fj prime plus sigma ak fj plus k, where k goes from 0 to 2, equal to order of something, right? That means we are given, let us say we want to make use of fj plus 1 and fj plus 2, right? That's what this is going to be. Sigma k equals 0 to 2, ak fj k is going to involve k equals 0 is going to give you fj, k equals 1 will be fj plus 1, and then k equals 2 will be fj plus 2. So given this stencil, can we calculate what is fj plus 1? That means how can you find the first derivative of f at the point j? So what is the maximum possible order of accuracy that we can achieve with these 3 points, okay, that we will make use of? So the function values are given at j plus 1, j plus 2. You need to calculate the derivative to maximum possible order of accuracy. So for that, what we're going to do is that we're going to build this Taylor table. And so essentially what the idea is, basically calculate the coefficients ak such that fj prime can be obtained, right, to whatever is this shown on the right hand side, to the maximum possible order of accuracy. Okay. So then I'm going to write this thing. So let me write essentially a Taylor table here. Okay, it contains some rows, that is fj prime, fj double prime, fj triple prime. Okay, so these are the so basically when I say fj prime, this is partial f by partial x at j. Okay, so we know that this is basically the same convention, and we're going to denote that my my grid is basically has h is the spacing. That means my delta x that I have is equal to h. Okay, and then what I have is, I have on the left hand side I have these terms. That is the first term I have is fj prime. Then after that I have essentially fj plus 1, fj plus 2, right? That's what it is here. So I'm going to fill up the table like this: fj prime, fj plus 1, and fj plus 2. Okay, that's what I have. So fj prime on the left hand side is basically going to have a 0 value for fj, 1 for fj prime, 0 for double prime, and 0 for triple prime, right? That's what I have. So I'm just filling up what will be the expansion of fj prime. Fj prime will be 1 times fj prime. Similarly, fj is going to be 1 times fj, and then it's going to be 0, 0, 0, right? That's what I'm going to get. Then fj plus 1 is going to be, because, okay, yeah, fj will not be 1, rather fj will be a0 times fj is what I'm going to get. So this is going to be a0, right, times fj is what I would get for the fj term. And fj plus 1, the coefficients will be what? Will be fj, right? So you'll have this is going to be a1 fj plus 1, right? a1 fj plus 1 when you expand it out. So I'm kind of writing it here for the sake of understanding. So this is like the previous, whatever we learned in the previous lecture. So when I write a1 fj plus 1, this is more like f1 a1 times fj plus h times partial f by partial x. That means fj prime plus h square by 2 factorial times fj double prime plus h cube by 3 factorial times fj triple prime, and so on, right? That's what we're going to get. That means I can expand a1 fj plus 1 as a1, right? That is going to be a1 times fj. So fj is in the numerator here, in the top row here, and then fj prime is going to be A1H. Fj double prime coefficient will be A1 H squared by 2. Fj triple prime is going to be A1 H cubed by 6. Okay. Similarly, Fj plus 2, when you expand, is going to be A2, right? I have written AK. So K equals 2. A2 Fj plus 2 is going to be A2 times, there will be an Fj value. Then it will be A2 times, this is now off by 2 delta x or 2h. So this is going to be A2 times 2h will times Fj plus 1 will be the next term. Similarly, the other term is going to be A2 times 2h square by 2 factorial, right? And then there's going to be A2 times 2h cubed by 3 factorial, right? That's what we're going to get. Okay. So this is the Taylor table, which we try to populate. Now, the idea is that essentially, we want to obtain, on the left-hand side, we want to obtain, essentially Fj prime plus all these, A0 Fj and so on. Okay, let me write this as A0 Fj, A1 Fj plus 1, A2 Fj plus 2. Okay, that is better. Okay, so this first column here is now denoting what we have for the LHS, right? So this is basically sum of the LHS, right? This is Fj prime plus sigma A K Fj plus K, right? That is the expansion. So, and then these terms are now written in a compact way in this table, right? Okay. So then if I want to equate the LHS, this is the LHS to RHS, essentially I have to sum all these things, right? Of course, there can be Fj4 and so on, but we are not writing all of them. That means if I sum these columns and then sum these rows, then that is going to give me whatever is there on the LHS, right? So that means I can write my Fj prime plus sigma K equals 0 to 2, AK Fj plus K equals is on the left hand side, right? That is the sum of this entire column. Then on the right hand side, what I have is A0 plus A1 plus A2 times Fj. So I'm summing this thing. This is A0 plus A1 plus A2 times Fj. Plus I have 1 plus A1H plus A2 to H. 1 plus A1H plus A2 to H times Fj prime. That is this quantity plus Fj double prime is going to be A1H square by 2. A1H square by 2 plus A2 2H square by 2 times Fj triple prime plus, then what I have is A1H cube by 6 plus A2 2H cube by 6 times Fj triple prime, right? So this is going to be A1 H cube by 6 plus A2 2H cube by 6 times Fj triple prime plus and so on. Okay. Now we want to obtain whatever is the maximum possible order of accuracy. What I should do is just like what I have done before, I need to set as many coefficients on the right hand side to 0 as possible. Okay. Now you see that we are able to obtain this equation in a much more straightforward and much more quick way rather than what we have done before. Like if you recall earlier, what we were doing is that we were writing these expressions. We were using Fj plus 1 expansion, Fj plus 2 expansion, prime expansion, all those things. Then we were using these free parameters, alpha, beta, gamma, and so on to multiply with all these values. And then essentially we are expanding, not primes, we are expanding Fj plus 1, Fj plus 2, and so on. And then we were essentially using these alpha, beta, gamma to make a linear combination of Fj plus 1, beta times Fj plus 2 plus gamma times Fj and so on, something like that. And then we are obtaining an equation. So that equation is essentially a modified version of this equation, right? What we are seeing here. Okay. So, but we are able to get to this much more quickly than what we have done before. Okay. Now, so now I need to set as many coefficients to 0 as possible. That means I will set on the right hand side this terms equal to 0, this equal to 0, and this equal to 0, because I have only 3 free coefficients. I will set the first 3 terms to 0. That means we have A0 plus A1 plus A2 equal to 0. And then we have A1H plus A2 2H equals -1, right? I write 1 plus this thing, I send the right hand side. And then we have A1H square by 2 plus A2 2H square by 2 equal to 0. Okay, so we have these 3 terms that is set to 0. Then we are left with essentially Fj triple prime here. Oh, sorry. Fj, this is double prime, right? This is double prime. Then we are left with Fj triple prime, but we cannot set this thing to 0 because we only have 3 coefficients. So we are setting this to 0 with a hope to maximize the order of accuracy. Okay, then once we calculate these A values, which we have done before, right? So these will come out to be exactly same as before. I have just worked them out. A1 equals minus 2AH, A2 equals 1 by 2H, and A3 equals 3 by 2H is what we would get. Then you can go back and substitute for A0, A1, A2 in the left-hand side. That's going to give you Fj prime plus sigma AK, Fj plus K, K equals 0 to 2, right? Substitute for this A0, A1, A2, A3, or actually it's basically supposed to be A0, A1, A2, A0, A1, A2, not A1, A2, A3, A1, A2, right? So substitute for these, then you're going to get a formula with a little bit of rearrangement. You're going to get Fj prime is going to be minus 3 times Fj plus 4 times Fj plus 1 minus Fj plus 2. Right, this is exactly same as what we got before, the forward difference formula, plus you're going to get order H square. So that means if you are given a stencil that is composed of Fj, Fj plus 1 and Fj plus 2, then the maximum possible order of accuracy you can get for the first derivative is only second order accurate, right? Okay. So now, of course, this is what we have already proved in the last lecture also, but through a different way, right? We have taken the linear combination and so on. Okay, but this is a somewhat a shorter way to get to these things. Okay, fine. So keeping this in mind, because this may be useful for us in deriving, you can either derive it the way we have done in the last lecture or in this way. Both are fine if you're able to, if you're comfortable. But this is a little more compact, and we can derive some advanced schemes, numerical schemes with this approach, with the Taylor table approach. Okay, any questions so far on this before I move on to the assessment of the error?
Seems okay, sir. Basically,
Okay.
it's a generic for like expression for the steps that we have discussed before in that.
Yes, I mean earlier we were doing it a little bit more expanded. We were expanding the Taylor series. Now we, instead of expanding the Taylor series explicitly, we are trying to write the coefficients directly with the Fj prime, Fj double prime in there.
Right.
Yeah.
Thank you, sir. Thank you.
Thank you. Okay. So then let's move on to, okay. So then we have also said with this order of H square, we said this is also some kind of a, for a scheme, we said this is also a truncation error because we are truncating this particular term. And we said that this particular scheme that we have derived, this is a forward difference scheme for the first derivative to second order accuracy. That means, as we discussed before, if you're going to make your mesh from delta x to delta x by 2, then your truncation error is going to become truncation error by 4 because this is a second order accurate scheme, right? It's going to decrease by 1 upon 2 square, right? Similarly, if you had a fourth order scheme, your truncation error would go down by 1 upon 2 to the power 4. That means it will go down by 1 upon 16, right? And so on. So truncation error basically gives you a relative sense for the error to how the error behaves. Okay. Now, looking at the truncation error is only one way of assessing the accuracy of the scheme. Okay. We will look at an alternative way of assessing the accuracy of a finite difference scheme. Okay, so what is an alternative way? An alternative way is basically is somewhat useful sometimes, especially in the solution of in the calculation of use of finite difference schemes, because it will provide you some more information in terms of how a particular scheme is going to behave when you are dealing certain type of functions or dealing with certain functions, and these functions happen to be sinusoidal functions. Okay, Now, why are we looking at only sinusoidal functions? Because essentially, if you look at Fourier representation, in Fourier representation, any function f of x can be expressed in terms of a Fourier series, okay, or using Fourier notations. Now, Fourier functions make use of the sinusoidal functions, right? So as a result, looking at sinusoidal functions will help us in applying it to any function that we are given. And we want to see if I'm going to apply this particular finite difference scheme to a particular f of x, how is it going to be accurate or not? How is it going to behave? So that's what we're going to look at. So essentially, we boil down the question that we want to look at accuracy of the finite difference scheme as applied to some kind of some sinusoidal functions. Okay, so the representative we will take for this is basically f of x equals e to the power I k x. Okay, where I is your essentially the complex number, right? This is basically equal to square root minus 1, right? So this is e to the I kx. We are using e to the I kx because this is basically equal to cosine kx plus I times sine kx. So this is your f of x. Okay, so this is a representation of a Fourier series, or it basically a function f of x, which we are taking it as e to the power I kx. Okay, where k is your wave number, or we can also call it as the frequency. So that means k can be written as 2 pi by L times n. Okay, that means n can go from 0, 1, 2 all the way to n by 2. Let us say. Okay, so what is this wave number? This wave number is basically if you have a domain of length L, right? If you have a domain of length L, then in this domain, how many waves of period 2 pi period can I fit, right? Essentially, how many waves of period 2 pi can be fit? Okay. That means if n equals 0, we are unable to fit even a single wave, but n equals 1, then we are essentially k is 1. That means we are able to fit 2 pi. That means waves of period 2 pi, one wave of period 2 pi in a length of L. Okay. Similarly, if n is equal to 2, then we can fit in 2 waves of period 2 pi in a length of L. That means it is varying much more rapidly. Similarly, if n happens to be, let us say, n by 2, then we can fit in n by 2 waves of period 2 pi in a length of L. Okay, so that means this basically is tells you how fast the function is varying. Okay, okay. To give you a better perspective, let me draw in a length of L. Let us say if I have n equals 0, n equals 0 is basically going to give me n equals 0 will be k equals 0. That means I have just k equals 0 is basically going to give me f of x equals e to the power I k x. K equals 0, e to the power 0 is going to be 1. So essentially this is going to be, there is no wave as such, right? There is basically a constant value. It's a constant value. This is n equals 0. But then if I have n equals 1, that is going to be, I'm going to fit n equals 1 is going to give me 2 pi by L. That means I can fit, let us say if I look at the cosine part or the sine part, one of them, let us say if I look at the sine part, then I can fit in essentially, if I'm going to 1.0, then I can fit in a sine that goes like this, right? I can fit in one way, essentially wavelength as such, or a period of length L. Okay. Similarly, let us say if I have this one going as 2, n equals 2, then I can actually fit in maybe 2 waves, right? That means I can essentially fit in something like that, right? So I have, this is one period, this is one period, and so on. So that is how, what I can fit in. So that means if I have n by 2, then essentially I have, okay, I should draw it a little better. Then what I have is I can fit in waves that are much more varying quickly. That means if I have n by 2, I can fit in wave something like that. Each wave is basically has a wavelength of, essentially 2 times delta x, okay, or 2 times h. So essentially, it basically gives you a sense for how oscillatory the function is. Okay, that means if I increase my k, my function is much more oscillatory in that domain, right? If my k is small, then I don't have a very large wave number. The function is slowly varying. Now, we want to know if we want to apply a particular scheme. Let us say we want to apply central difference scheme, which is second order accurate to a particular function that is slowly varying. How does it going to behave? If a particular function is varying very quickly, how is it going to behave? That's what we want to look at. In general, of course, as you can already know, that in general, when we deal with nonlinear differential equations, okay, the functions that we would get typically will have a range of wave numbers. Okay, that may go from small to large. So, but then we should be able to capture all these values when we take a derivative of that. But then we will see if the corresponding finite difference scheme we have is going to faithfully or correctly represent the derivative at small wave numbers or at high wave numbers or at both of them or at none of them. Okay, that's the question. Okay, that's what we're going to look at. So for that, what we define is we define something called a modified wave number. Okay, and this approach is called the modified wave number approach or method, which is going to tell us that if we are dealing with a particular wave number, which theoretically we want to deal with, what is this value as the numerical scheme is applied? Okay, as we apply a particular numerical scheme, that means as we apply a particular derivative, what is the modified wave number that we're going to get? Is it going to be the same as k, or is it different from k? If it is going to be different, then it is not good because it's not going to capture the derivative correctly. Okay. So before that, I'll go back to this function. That means what we have written is we have said essentially f of x equals to e to the power ikx. This is the function I want to calculate, and then of course I want to calculate the derivative f prime. F prime is basically d by dx of e to the power ikx is basically going to be I times k times e to the power ikx. But then there's going to be e times k, but e to the power ikx we already have written as f of x. So this is f of x. That means f prime is simply I times k times f of x. That means if you want to calculate the derivative for this function, so analytically the derivative is simply multiply the function with I times k, and that is going to give you the derivative. Okay, but then what is k here? K is the wave number. Okay, so we want, if we are able to get k for any numerical scheme, that means this is analytically is what we have calculated. If I'm going to calculate f prime numerically using, let us say, some scheme, either a central difference scheme, then what will be the wave number for that scheme? Then I'm going to compare the wave number that scheme gives to the theoretical wave number that we should obtain. Okay, then I'm going to can tell my solution, my derivative is going to be accurate for these range of wave numbers, and it is not going to be accurate for the other range of wave numbers, and so on. Then let me take the x-axis, right? The x-axis is there, and then we are going to now discretize a portion of the x-axis of length L, okay, with some points. So we're going to say that my delta xj, which is my h, is going to be L divided by n times j, right? So let us say I have points from 0, 1, 2, all the way to n minus 1 and n. Okay, so to n minus 1. Okay, so that's where my domain ends. So this is where my L ends. Okay, so I have from 0 to n minus 1. So my delta xj, which is also equal to h, is nothing but length divided by number of points. Number of points is 0 to n minus 1, that is n points, and then times j. So that means this is my interval, and then when I multiply with j, this is going to give me what is the x location, right? So this is nothing but delta xj equals h times j. That means each interval is h, and so on. Okay, so that is what I have. Okay, so that is what my delta xj is. Then let me also apply what is a particular scheme. So let me apply, let us say, central difference scheme. That means I want to calculate what is delta f by delta x at a particular point j. Okay, so this is going to be, as we have seen before, this is f of j plus 1 minus f of j minus 1 divided by 2h plus order of h square, right? So this is our derivative, first derivative using central difference scheme to second order accuracy, right? So this is the simplest we can write. But then my f of j is what? My f of j is basically, I can, from here I can write it, f of j is nothing but e to the power I k x j, right? So this is going to be e to the power I k x j, but e to the power k is nothing but by 2 pi by L times n. My xj is nothing but, I have just defined it here, is going to be L divided by n times j, in which case I can cancel my, I can cancel this L, and then what I end up with is f of j equals e to the power I 2 pi n divided by capital N times j. Okay, where here j denotes the grid point, I denotes the complex number square root minus 1. Okay, fine. Then similarly, now I want to calculate, I have represented this delta f by delta x. This is basically to represent the numerical derivative. Okay, so which is nothing but fj plus 1 minus fj minus 1 by 2h. Now, what would be fj plus 1? Fj plus 1 is going to be e to the power I 2 pi n divided by capital N times j plus 1. Similarly, fj minus 1 is going to be e to the power I 2 pi n divided by capital N times j minus 1. That means if I were to calculate this delta f by delta x at point j, this is going to be, as per the formula, fj plus 1 minus fj minus 1 divided by 2h. This is nothing but e to the power I times 2 pi little n divided by capital N j plus 1 minus e to the power I times 2 pi little n by capital N times j minus 1 divided by 2h. Okay. Then in both these functions, e to the power I 2 pi n times j is common, right? I have 2 pi n j here, 2 pi n j here, so which I can take it out. Then I end up with e to the power I 2 pi little n by capital N, because I have plus 1 here and then I have minus 1 here. We'll have minus e to the power minus I 2 pi n by capital N because of this minus 1, okay, divided by 2h times, for both functions we have taken out the common e to the power I 2 pi n by capital N times j. Okay. Now, this is numerical derivative, delta f by delta xj equals, okay, what is e to the power I 2 pi little n by capital N times j? I 2 pi n little n by capital N j is nothing but fj, right? So this portion is fj, this is fj times, what I have here is e to the power I theta minus e to the power minus I theta, right? This is going to be, is nothing but e to the power I theta plus e to the power minus I theta. E to the power I theta is nothing but cosine theta plus I sine theta, plus e to the power minus I theta is nothing but cosine theta minus I sine theta. So, oh, sorry, we have a minus here. So we have a minus, it is a minus here. So this is going to be, this is a minus, this is going to be minus, this is plus. This is going to be 2I sine theta because the cosine terms get cancelled. That means this is nothing but 2 times I sine, my theta is nothing but 2 pi little n by capital N divided by 2h, right? That is the expression for delta f by delta xj, okay? So if I were to rearrange, I can cancel 2 from here. So what I get is essentially my numerical derivative using second order accurate central difference scheme for the first derivative is delta f by delta xj equals I times, right, sine 2 pi little n by capital N divided by h times fj, right? So this is what I got for my numerical derivative. Okay, but what did we get for the analytical derivative? Analytical derivative, which we have done before, fj prime was I k times f of x. That means if I were to write it for j, fj prime equals I times k times fj, right? For any grid location, fj prime equals I times k times fj. If I were to write it just below this thing, fj prime equals I times k times fj is what we got. So here you can see a comparison between the numerical derivative and the analytical derivative. We have I, fj, fj. So what we have is here is instead of k, we have this quantity, which is the wave number. Now this wave number is not k, this is something else. That means what we have, if I were to compare, that means what I have is this is my this quantity I have here is my numerical or modified wave number, which I would like to represent as k prime. Okay, so this is the modified wave number, which I will get when I try to solve for the derivative using a central difference scheme that is second order accurate. Now, of course, if you use a different scheme with different order of accuracy, you're going to get a different modified wave number. So I'm calling this coefficient that is in between I and fj as k prime. Let me call this as sine of 2 pi little n by capital N divided by h. Okay. Okay. So, but then let me also rewrite this thing. So this is going to be sine 2 times pi into let us say divided by n, okay, into n is what I got, okay, so 2 pi n, but then what is my delta x? My delta x or my h? Okay, so my L by n is j. Okay, so that means if I can study what is this for different n values, then I know how is my modified wave number k prime is going to behave in comparison to k. Okay, so I want to bring in let me write this as k prime times h. That means let me take it to the left hand side. This is going to be sine of 2 pi little n by capital N. Is what I got correct. Okay, so this is fine. 2 pi n by n is what I got. Okay, so but what is h? H equals, from what I have before. Okay, my h equals L by n, right? That is what I have. Okay, and then my k equals, which we have done before, this is 2 pi by L. Okay, so I can rewrite this thing with these two definitions that we have used. My wave number k equals 2 pi by L, and then my h equals L by n, right? That is the length divided by number of points. So if I were to write k times h, that is going to be 2 pi by n, right? Because L will get cancelled. So this quantity 2 pi by n is nothing but h. So this means k primes h equals sine of kh times n, right? Oh, sorry. Okay, so sine of kh times n is what I get. Will the n also be absorbed? I think the n also should be absorbed somewhere. Oh no, k equals 2 pi n by L, right? I'm studying it for different k values. So if n, where n goes from 0, 1, 2, 3 all the way to n by 2, that's going to give me a range of functions k, right? So this is already absorbed. So my 2 pi n by capital N is nothing but my k times h, right? So I have defined k equals 2 pi by L times n. We go back, right? K equals 2 pi by L times n, where depending on the n value, I'm getting different functions. Now, different functions are nothing but different e power ikx, which are nothing but different f of x, right? I'm looking at functions that are varying slowly for small values of k. I'm looking at functions that are varying rapidly for large values of k, okay? So what we got is essentially k prime h equals sine of kh, okay? Okay, so that means if I were to look at how does the modified wave number going to look like in terms of the actual wave number, then I can comment on how this particular central difference scheme is going to behave for slowly varying functions and rapidly varying functions. That means let me draw a graph here, something like this. Okay, on the x-axis, let me take the modified wave number. I'm plotting k prime times h. On the y-axis, on the x-axis, I'm plotting k times h. Now, if if these, if my k prime h equals kh, let me also choose a range for this thing. Let me say this is 0 to pi, that is equal to 3.1415. And then on the y-axis, we have up to pi. Okay, so we have 0, this is pi by 2. Let's say this is 1, this is 2. Similarly, I have 1, I have 2, something like this. Okay, so if I were to, if my k prime h equals kh, that means I have y equals x line. That is nothing but essentially a 45-degree line, right? That is, this is my exact, this is the exact solution, right? If I had used a analytical solution, my k prime h equals kh, that means the modified wave number equals the original wave number. But then if I had used this scheme, that is k prime h equals central difference scheme, that is second order accurate, then my k prime h is only equal to sine of kh. That means sine of kh is on the x-axis. Let's say this is like sine theta. Then it is going to reach a value of maximum of 1 at pi by 2. That means at pi by 2, it's going to reach a value of 1. Okay, and it's going to decrease, and it's going to increase to this value and then decrease. So my k prime h is only going to go something like that. Okay, I have drawn it. So it's going to match a little bit here, and then it's going to deviate. That means this is for the central difference scheme. How does the modified wave number going to look like? So as you can see, if I am at the small wave number region, then my modified wave number is very close to the exact wave number, and that is not going to cause any problems, right? But if I go to high wave number range, where my k is larger, then the modified wave number changes considerably from the exact wave number. As a result, it is not going to resolve, or it is not going to calculate the derivative correctly, right? That means for slowly varying functions which have low wave number, central difference scheme will work fine. If I have highly varying functions which have high k, then central difference scheme is going to introduce errors. Okay, that is the takeaway from here. Now, as you can see, we can always make a high wave number value to be still, we can make the CDS calculate the errors with less errors by multiplying with h, right? So even if I have a high value, I can take my grid to be finer and finer and finer, such that this k times h will become small, and it is going to lie in this region, right? Then again, the CDS will start giving you correct derivative values, even if you have a highly varying functions. But then this h can be very large, right? Because your h has to be essentially 1 over the k or pi over k, such that your CDS will start working. So as a result, many of these schemes will perform, many of the finite difference schemes perform well when you are dealing with slowly varying functions. They do not accurately calculate the derivative values when you are dealing with highly varying k values. Now, on this plot, we can also make another plot. Let us say if you were to calculate a central difference scheme for the first derivative using fourth order accuracy, then you can make exactly like the same steps as I have done, and then calculate what is delta f by delta xj using a fourth order accurate central difference formula that involves essentially fj plus or minus 1 and j plus or minus 2 and so on. That will give you a different modified wave number k prime h in terms of something that is going to look like something like this. It's going to match with k for a little larger thing, and then it's going to come down. Okay, so that will be for a fourth order central difference scheme. That means it can, up to a larger wave number times h value, it can accurately give you the derivative values. But then as you go to higher wave numbers or higher frequencies of functions, then again it's going to deviate and it's going to give you errors. Okay, so that is what is going to happen. Okay, so tomorrow we're going to look at a particular class of schemes which are known as Pade schemes, which have slightly better properties than the central difference schemes or these one-sided schemes and so on. Okay, using this, we're going to essentially comment on that. Fine. Okay. If you guys have any questions, you can ask me. Otherwise, I'm going to stop here. And I'll catch up with you tomorrow. Any questions, anybody?
Sir, we have to just assimilate a bit and then we
Sure.
come back.
Yeah, I think these are little new concepts because we use this e power I theta, wave number, all those things. But you can certainly go through this thing. It is useful because we can then think of different functions, how derivatives behave, in the context of highly varying and slowly varying functions.
Sure, sir.
Yeah, because what will happen in practice is that you have written a code for a derivative. This derivative will give you correct answer when you have sin x function. When you have sin 100x, it is not going to give you correct answer because sin 100x will vary very, very fast. So your answer will be incorrect. Then you would wonder where is my mistake, but the mistake is not in the code that you have written, but rather in the theory that is there in terms of the scheme itself. The scheme itself cannot capture any highly varying k. So the moment you start applying to higher and higher frequency content functions, it will start deviating from the correct answer. Yeah, I would suggest all of you to kind of, review this and then come back with questions. Fine?
Totally fine, sir. Thank you.
Sure. Yeah. Any other questions? Anybody? Comments? Okay, if not, I'm going to stop here. Thank you, guys. I'll see you tomorrow. We will look at Faraday schemes and then look at develop a procedure for calculating truncation error for a given governing equation. Okay, so that's what we'll look at tomorrow. Fine. All right. Thank you, guys. I'll stop here.
Thank you.
Thank you, sir.
Thank you.